Welcome to this problem walkthrough. In this session, we'll dive into the problem number 1461, check if a string contains all binary codes of size k. We'll explore different approaches to solve this challenge, analyze their complexities, and discuss the key concepts involved. Let's get started. In this problem, we are given a binary string s and an integer k. The task is to determine whether all possible binary codes of length k can be found as substrings within the string s. If all such binary codes are present, the function should return true. Otherwise, it should return false. The input consists of a binary string, which is made up of characters 0 and 1, and an integer k that specifies the size of the binary codes we need to check for. The output is a Boolean value that tells us if every binary code of size k is a substring of s. To better understand this, let's look at some examples. In the first example, the binary string s is 00110110 and k is 2. This means we are checking for all binary codes of length 2. The possible binary codes of length 2 are 2000 foot, 01, 10, and 11. Now, if we look at the string s, we can find each of these codes as substrings. For instance, 2000 foot is found at indices 0 to 1, 01 is found at indices 1 to 2, 10 appears at indices 2 to 3 and again at 4 to 5, and 11 is located at indices 3 to 4. Since all four binary codes of length 2 are present in the string, the function returns true. For the second example, s is 0110 and k is 1. Here, we are checking for all binary codes of length 1, which are simply 0 and 1. In the string s, 0 appears multiple times at indices 0, 2, and 3, while 1 is found at indices 1 and 2. Since both 0 and 1 are present in the string, the function returns true. This demonstrates that even with smaller values of k, the binary codes can still be checked effectively. In the third example, the binary string s is again 0110, but this time k is 2. Now, we are looking for all binary codes of length 2, which are 2000 foot, 01, 10, and 11. In the string s, we can find 01 foot at indices 0 to 1, 11 at indices 1 to 2, and 10 at indices 2 to 3. However, the code 2000 foot is missing in the string. Since not all binary codes of size 2 are present, the function returns false. This example highlights that even if most codes are present, missing just one code leads to a false result. Now let's consider some edge cases. If the value of k is greater than the length of the string s, it's impossible to find any substring of size k, so the function should return false. If k is 1, we only need to check for the presence of 0 and 1, which is straightforward. Finally, when the length of s is very large, close to 10 to the power of 5, the solution must handle this sufficiently. This means we should avoid explicitly generating all possible binary codes of size k, as this could be computationally expensive. Instead, the algorithm needs to be optimized to check for the presence of these codes in a more efficient manner. To tackle this problem, the most straightforward approach is the brute force method. The intuition here is simple: we generate all possible binary codes of size k, which amounts to 2 to the power of k possibilities. Once we have these codes, we check if each one is a substring of the given string s. The process involves two main steps: first, generating all 2 to the power of k binary codes, and second, iterating through each code to see if it appears in s. While this approach is intuitive, it becomes computationally expensive as k grows. Generating all binary codes alone takes 2 to the power of k time, and for each code, checking its existence in s requires n, where n is the length of the string. This results in a total time complexity of 2 to the power of k asterisk n, which is impractical for larger values of k because the number of binary codes increases exponentially. Thus, while easy to understand, this approach struggles to scale efficiently and has significant performance drawbacks for larger inputs. To address the inefficiencies of the brute force method, we can adopt a more optimized approach using a sliding window combined with a hash set. The intuition here is that instead of generating all possible binary codes explicitly, we extract all substrings of length k directly from s using a sliding window. As we slide through the string, we add each unique substring to a hash set, which handles duplicates automatically. Once we've processed the entire string, we simply check if the size of the hash set matches 2 to the power of k, the total number of unique binary codes of size k. If it does, we know S contains all the binary codes, so we return true. Otherwise, we return false. This method is significantly more efficient because sliding through the string takes O, n, and hash set operations like insertion and size checks are O, 1 on average. Additionally, we can stop early if the hash set size already reaches 2 to the power of k, as we don't need to process further. This approach ensures we only extract and store unique substrings, making it much faster than brute force while maintaining correctness. The sliding window approach offers several advantages over brute force. It is much faster because we avoid the step of explicitly generating and checking all 2 to the power of k binary codes. Instead, we focus only on the substrings present in the string S, which reduces unnecessary computation. This makes it scalable even for larger values of k, where the brute force approach would become infeasible. However, there is a trade-off. The sliding window technique requires additional space to store the hash set, which has a worst-case space complexity of O(2 to the power of k). While this is acceptable for smaller values of k, it could become a limiting factor if k is very large. Despite this drawback, the method balances time and space efficiency well for most practical scenarios, making it a significant improvement over the brute force approach. Given the trade-offs and benefits, the sliding window with hash set approach is the chosen strategy for solving this problem. The brute force method, while conceptually simple, is impractical for large values of k due to its exponential time complexity. In contrast, the sliding window approach is far more efficient, as it extracts substrings in a single pass and avoids the overhead of generating all possible binary codes. The use of a hash set ensures that only unique substrings are stored, simplifying the task of verification. However, this method does trade off space for improved time efficiency, requiring O(2 to the power of k) space in the worst case. While this space complexity is manageable for reasonably small values of k, it may become a challenge for very large k, such as k equals 20. Still, for most practical scenarios, this method strikes an effective balance between time and space efficiency, making it the optimal choice for solving this problem. The problem we're solving involves a string S and an integer k. Our goal is to determine if every possible binary code of length k exists as a substring within S. To tackle this, we can start with a brute force approach. First, we generate all possible binary codes of size k. Since there are 2 k codes, we can produce them by counting in binary. For instance, when k equals 2, the codes are 0, 0, 0, 1, 10, 11. Next, for each binary code, we check whether it exists as a substring in S. This involves scanning the string for each code, which takes linear time for each search. By systematically generating and verifying all codes, we can determine if the condition is met. Once we've checked all the binary codes, we return the result. If every single binary code is found as a substring in S, we return true. Otherwise, we return false. Let's consider an example to clarify this process. Suppose the input is S equals 00110110 and k equals 2. First, we generate the binary codes of size k, 00, 01, 10, 11. Then, we check each code against the string. The code 00 is present in S, as are 01, 10, and 11. Since all codes are accounted for, the result is true. This method is straightforward but can become inefficient for larger values of k due to the exponential number of codes to generate and check. The brute force approach, while simple, has significant limitations in terms of efficiency. Generating all binary codes requires O(2 to the power of k) time, and for each code, searching through the string S takes O(n) time. This leads to a total complexity of O(2 to the power of k*n, which becomes impractical for larger values of k. To address this, we can optimize the substring search step. By pre-processing the string S, we can reduce the time required to check for the presence of binary codes. For example, instead of generating all possible codes explicitly, we could use a set to store and retrieve substrings more efficiently. This allows us to streamline the search process and avoid redundant computations. To optimize further, we can use the sliding window technique. By sliding a window of size k across the string S, we can extract all substrings of length k in just O(n) time. These substrings can then be stored in a hash set, which provides O(1) average case time for insertions and lookups. This approach eliminates the need to explicitly generate all 2 k binary codes. Instead, we can simply compare the size of the hash set to 2*k. If the set contains exactly 2*k unique substrings, it means all binary codes are present and we return true. Otherwise, we return false. This method is both efficient and elegant, leveraging the properties of hash sets and sliding windows to minimize redundant computations. The optimized approach significantly improves complexity. Extracting substrings with a sliding window takes O(n), while hash set operations like insertions and lookups are O(1) on average. The total complexity is therefore O(n plus 2 to the power of k), which is much more manageable compared to the brute force method. Let's revisit the example with s equals 00110110 and k equals 2. Using a sliding window, we collect the substrings 00, 01, 11, 10, which are stored in a hash set. The set now contains 4 unique substrings. Since 2*k also equals 4, we confirm that all binary codes are present and return true. This approach not only reduces time complexity but also simplifies the implementation, making it well suited for larger inputs. This solution checks if a string contains all binary codes of size k using a sliding window technique and a set to track unique substrings. Here's the detailed explanation. 1. Initialization. A set scene is created to store unique substrings of length k. The total number of possible unique binary codes of size k is calculated as 2*k, or 1k for efficiency. 2. Sliding window. The algorithm iterates through the string s using a range defined by len s, k plus 1. For each position I, it extracts the substring s, I plus k, of length k and adds it to the scene set. This ensures that only unique substrings are stored. 3. Early exit optimization. If the size of the scene set matches total underscore codes, i.e., all possible binary codes have been encountered, the function immediately returns true. This avoids unnecessary iterations once the condition is satisfied. For final check, if the loop completes without finding all codes, the function checks if the size of scene equals total underscore codes. If not, it returns false. This approach is efficient because the sliding window ensures each substring is processed in O(1) time, resulting in an overall complexity of O(n), where n is the length of the string. The use of a set guarantees uniqueness of substrings without additional overhead. Edge cases such as k-len s are naturally handled since the loop won't execute in such scenarios. This is the Java implementation of the LeetCode problem number 1461, which checks if a string contains all binary codes of a given size. The logic mirrors the Python solution, using a hash set to store unique substrings of the required length and ensuring that the total number of unique binary codes matches 2 to the power of k. Key Java-specific differences include type declarations, the use of Java's hash set, and the substring method for string manipulation. In this example, we are given the string s equals 00110110 and k equals 2. Our goal is to determine if the string contains all possible binary codes of length 2. First, we calculate the total number of unique binary codes of size 2, which is 2*2 equals 4. These codes are 00, 01, 10, 11. To solve the problem, we initialize an empty set called scene to keep track of the unique substrings of length k that we encounter, and we set total underscore codes to 4, which represents the total number of binary codes we need to find. This setup prepares us to iterate through the string and check if all the required codes are present. Now, we begin iterating through the string to extract all possible substrings of length k equals 2. Starting with I equals 0, we extract the substring s, 0:2, equals 00 and add it to the scene set. At this point, scene equals 00, and the size of the set is 1, which is less than total underscore codes. Next, for I equals 1, we extract s, 1:3, equals 01 and add it to the set. Now, scene equals 0001, and its size increases to 2, still less than total underscore codes. Continuing, for I equals 2, we extract s, 2:4, equals 11 and add it to the set, resulting in scene equals 0001, 11, with a size of 3. Finally, for I equals 3, we extract s, 3:5, equals 10 and add it, making scene equals 0001, 10, 11. At this point, the size of the set equals total underscore codes, meaning we have found all the required binary codes. Therefore, we return true. In this second example, the string is s equals 0110 and k equals 2. Again, we need to determine if the string contains all binary codes of length 2, with total underscore codes equals 2 squared equals 4. We initialize an empty set scene to store the unique substrings of length 2, and we set total underscore codes to 4. The iteration begins with I equals 0, or we extract the substring s, 0 to 2, equals 0, 1 and add it to the set, resulting in scene equals 0, 1. The size of the set is now 1, which is less than total underscore codes. For I equals 1, we extract s, 1:3, equals 11 and add it to the set, giving scene equals 0, 1, 11, with a size of 2. Next, for I equals 2, we extract s, 2:4, equals 10 and add it to the set, resulting in scene equals 0, 1, 11, 10. The size of the set is now 3, which is still less than total underscore codes. At this point, we have reached the end of the string, but the size of the scene set is still 3, which is less than the total underscore codes equals 4. This means that the string does not contain all the unique binary codes of length 2. Therefore, we return false. Moving on to a new example, we are given the input s equals 00000000000 and k equals 3. Here, the total number of unique binary codes of size 3 is 2⁻3 equals 8. To solve this, we initialize an empty set scene to track the unique substrings of length 3, and we set total underscore codes to 8. This setup allows us to begin iterating through the string and checking for all possible binary codes of size 3. As we start iterating through the string, we extract substrings of length 3 from s. For I equals 0 to I equals 7, the substring extracted is always 0, 0, 0, since the entire string consists of repeated zeros. Each time, we add 0, 0, 0 to the scene set, but since it is the same substring, the set remains scene equals 0, 0, 0. By the end of the string, the size of the scene set is 1, which is far less than the total underscore codes equals 8. This means the string does not contain all the unique binary codes of length 3, so we return false. Here, we break down the time complexity of the algorithm. First, we iterate through the string, with the loop running from the start of the string to a position where a substring of length k can still be extracted. This gives us approximately n iterations, where n is the length of the string. Within each iteration, we extract a substring of length k, which takes k times, and slicing in Python creates a new string. Multiplying the number of iterations by the cost per iteration, we arrive at n*k for substring extraction. Adding substrings to the set and checking its size are very efficient operations, with an average cost of 1 due to Python's hashing mechanism. While the loop may terminate early when the set contains all possible binary codes of length k, in the worst case, the entire string must be traversed. Therefore, the overall time complexity is dominated by the substring extraction, resulting in n*k. Now, let's analyze the space complexity. The primary space usage comes from the scene set, which stores unique binary substrings of length k. In the worst case, this set will contain all 2 to the power of k possible binary strings. Since each binary string has a length of k, the total memory required for the set is 2 to the power of k*k. Additionally, at any given moment, a temporary substring of length k is created during slicing, which adds an k memory overhead. However, the dominant term in space usage is the memory allocated for the scene set, so the overall space complexity is 2 to the power of k*k. When analyzing the best, average, and worst cases, we find that the algorithm's performance depends on the input string and the value of k. In the best case, if the string quickly contains all 2 to the power of k binary codes, the loop terminates early, and the time complexity becomes sublinear, though it still depends on k in the structure of the string. In the average case, the loop typically iterates through the entire string, yielding a time complexity of n*k. In the worst case, the loop processes all substrings and includes all 2 to the power of k binary codes, resulting in n*k time n 2 to the power of k*k space. Comparing this to a brute force approach, which involves generating all 2 to the power of k binary strings and searching each one in the input string, the current solution is much more efficient. The brute force approach has a time complexity of 2 to the power of k*n, which is significantly worse than the optimized n*k. Both approaches require 2 to the power of k*k space to store binary strings, but the current solution avoids the overhead of generating the strings explicitly. The optimized approach improves on the brute force method by directly extracting substrings from the input string and using a set to track unique codes. This avoids the need to explicitly generate all binary strings of length k, leading to better time efficiency. Mathematically, the substring slicing operation takes O, k, per iteration, and the loop runs for O, n, iterations in the worst case. Set operations, such as adding an element and checking the size, are O, 1, on average. Combining these, the overall time complexity becomes O, n asterisk k. For space, the dominant factor is the storage of up to 2 to the power of k binary strings of length k, resulting in O, 2 to the power of k asterisk k, memory usage. This combination of time and space efficiency makes the optimized approach far more practical than the brute force alternative in handling large inputs. When working on this problem, there are a few common mistakes to watch out for. First, not accounting for edge cases can easily trip you up. For example, if the string s is shorter than k, or if k is excessively large, it could lead to index out-of-bounds errors or unnecessary computations. To avoid this, always validate your input constraints before diving into the logic. Another mistake is using inefficient methods to search for substrings. For example, if you rely on nested loops, you could end up with a time complexity of O, n squared asterisk k, which becomes impractical for large inputs. Instead, optimize your approach using a sliding window or hash-based techniques. Lastly, errors in generating binary codes are also common. You might miscalculate the number of possible binary strings, forgetting that it should be 2 to the power of k, or you might accidentally generate duplicates. A good fix here is to use bitwise operations or leverage Python's itertools.product to ensure correct and unique binary code generation. Another mistake to be mindful of is assuming that the order of binary codes in the string matters. Remember, the problem only requires that all 2 to the power of k codes are present as substrings, not in any particular sequence. To address this, focus solely on checking for the presence of substrings rather than their order. Additionally, incorrect use of hash sets can cause issues. For instance, you might forget to clear or reinitialize the hash set between test cases, leading to stale or incorrect results. To fix this, always ensure you're starting with a fresh hash set for every test case. These small adjustments can make your solution much more robust and reliable. This problem is a great opportunity to showcase your understanding of key patterns often seen in interviews. Specifically, it combines substring search with combinatorial generation of binary strings of size k. Efficient solutions typically involve sliding windows and hash sets, so be sure to emphasize these during an interview. Focus on how you optimize from a brute force approach, which has a complexity of O, 2 to the power of k asterisk n, down to O, n asterisk k, with sliding windows and hashing. It's also a good idea to proactively discuss edge cases, like when k is greater than the length of s, when the string is empty, or when k equals 0. This demonstrates attention to detail. Finally, don't forget to communicate trade-offs. Explain why brute force is suboptimal and how the sliding window approach strikes a balance between efficiency and simplicity. For additional preparation, you might find it helpful to explore related problems like longest substring without repeating characters or minimum window substring, as these share similar concepts. There are a few alternative approaches you can explore for this problem. The brute force method is the most straightforward. Here, you generate all possible binary codes of length k and check each one against the string s. However, its complexity is O, 2 to the power of k asterisk n, making it impractical for large values of k. A more efficient method uses a sliding window combined with a hash set. With this approach, you slide a window of size k across the string, extracting substrings and storing them in a hash set. This method reduces the complexity to O, n asterisk k, but it requires careful implementation to ensure the sliding window operates correctly. For those seeking the most optimized solution, bit manipulation can be a powerful technique. By representing substrings as integers and using bitwise operations to slide through the string, you can achieve a time complexity of O, n. However, while this approach is highly efficient, it's less intuitive and can be harder to debug. Each method has its trade-offs, so consider the specific requirements and constraints of the problem when deciding which one to use. Thanks for joining us on this walkthrough. We've summarized the key points, takeaways, and techniques used to solve the problem. Keep practicing these concepts to strengthen your coding skills. Don't forget to stay connected for more engaging tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!